Good morning, everybody, and welcome to this talk, which is going to be given by Dr. Chloe Martindale. I'm Dr. Catherine Blackwell. I'm the head of the Faculty of Engineering's Industrial Liaison Office. This talk is part of our Faculty of Engineering Research Showcase. The purpose of this week-long event is to demonstrate the breadth of research capability that we have in engineering at Bristol. And we also hope that it will provide stimulus for conversation and hopefully future collaborations. Thank you for joining us today, and I hope that you enjoy the talk. I'm now going to hand you over to Chloe, and she is going to talk to you about post-quantum cryptography.
Thank you, Catherine, for the introduction. I'm going to share my screen because I've got some slides for you. As Catherine said, please do think about what you might like to ask about. I'm open to questions of all kinds, depending on how much expertise you might have. I'd be very happy to hear what you have to say about these topics. So yeah, I'm talking about post-quantum cryptography. So that's basically about the relationship between cryptography and quantum computers. So if you're attending some of the other sessions today, then perhaps you're quite up to date on what sort of things we can do with quantum technologies and what we hope we can do with quantum technologies in the future. And there's a lot of very exciting, positive things that will come out of quantum computing, and hence the excitement about developing that. But there's also a sort of scary side, which is its impact on cryptography, which some people in the community, including myself, are trying to solve before that becomes a very widespread problem. So in order to explain a little bit where this problem comes from and how to solve it, I'm first going to talk about what cryptography is and how we can sort of split that up into things that are broken by quantum computers and aren't broken by quantum computers. So what is this all about? So let's start at the beginning. What is cryptography? Well, on a very basic and simplistic level, what we're talking about here is we're talking about sending messages over an insecure channel that we want the message to be secure. So in this picture, we've got your favorite prince as the sender and your favorite princess as the receiver. Well, maybe not your favorite, but this is just some pictures I decided to use. And so you can imagine that Harry and Meghan are good examples of people who might want their messages to each other to remain private because it's something that media would pick up on and put all over the newspapers if they read them, no matter what was in them. And so when they're sending messages to each other on their phones or whatever it might be, it's very important these messages, the contents of these messages remain private. But when they're using, Wi-Fi or wired internet, the channel itself is not particularly secure. And the terminology that we use for this in cryptography is we say that there's an eavesdropper who we typically call Eve. And here's an example of an eavesdropper who is monitoring most channels in the world most of the time. That's the NSA from the USA, which is often used as an example among cryptographers because, well, it's a very powerful eavesdropper that has sort of unlimited computing power, where the limit is on human knowledge rather than anything else. So these are the problems that come with a channel being observed by an eavesdropper. So communication channels both store and spy on our data. So the storing is especially relevant for thinking about the impact of quantum computers, because a very powerful adversary like the NSA, for example, can store encrypted messages long-term for 20, 30 years, and then decrypt them at a later date. And if that contains information that you would still consider sensitive in 20 or 30 years, as quantum computers develop, then that becomes a problem even for now, right? It's not only a future problem. And there's another problem, which is a more present thing, and this is relevant for cryptography and will be relevant for post-quantum cryptography in the future, but it's less of a problem right now, which is that communication channels are modifying our data. So this is something that we can solve with what we call classical methods, which means using a non-quantum computer like your laptop that you currently use. Okay, so what are our goals in cryptography? We're aiming for confidentiality despite Eve's espionage, and we're aiming for integrity, recognizing Eve's espionage. So the confidentiality is mostly about the first one, right? So that's about an adversary not being able to view the contents of your message that you want to remain private. And integrity is mostly around the second one, which is if somebody is trying to impersonate you, you can recognize that you're being impersonated. So apologies, Sarah, but I said I was going to bring this up in the talk, so I might as well. Here's an example. So Sarah, who's helping out with this session, when she first joined it, for some reason, Zoom decided that her name was Chloe Martindale, but I could recognize that she was not Chloe Martindale because I'm Chloe Martindale. So this was an example where I could recognize that she was not who she said she was. But if I hadn't been here then, and you didn't know what I looked like and her video was off, this would be an example of how to impersonate somebody online. Okay, so that's what cryptography, roughly on a very simplistic level, is about. And now I'm going to talk a little bit about how we might achieve this, right? So if we have an insecure channel, how is it possible that you can send a message over that channel, but the contents of the message remain private? So again, I'm going to do everything on a sort of nice down-to-earth level, but I did want to explain a little bit how that might work. Okay, so this looks a bit technical, but bear with me while I talk you through it. So if you read the top example, encrypted messaging with one-time pads. So if you use online banking, for example, you might have noticed when you are logging into your bank or when you're sending a payment, sometimes it asks you for an OTP, and that OTP stands for one-time pad. So what does a one-time pad do? Well, that's something that your bank uses to encrypt your personal data to check that you are who you say you are, to let you take your money out, right? So this is an example of the integrity that we talked about. So how does that work to encrypt a message? So in this example, our message is a bit string. So that's just a list of zeros and ones. So here's a very simple example where you've got a 7-length bit string. And our one-time pad, our OTP, is also a bit string of the same length. And so that's K for key. This is like a key that we use to lock and unlock our message. So both the message and the one-time pad are things that we want to keep secret. So that's not something we send over the channel, but that's something that, for example, Harry has in his private data on his phone. He doesn't know that, but his phone computes that on its own. Okay, so how do we use the one-time pad to encrypt the message? And then this is the encrypted message that we'll send over the channel. Well, it's very simple. So to read the third bullet point, it says encrypted message, line up M and K. So that's the message and the key or the one-time pad. And we flip the bit of M, meaning we change it, if and only if the corresponding bit in the K, in the key is 1. So I've got a little diagram here at the bottom where the top line is M, the second line is K, and the bottom line under the arrow is the encrypted message. So how have we encrypted that message? We've just looked at the blue number, and if it's a 0, then we haven't changed the black number. And if it's a 1, then we have changed the black number. And then this gives us a different bit string, which is not the message and it's not the key. But if our receiver, Megan, in the picture we had, also knows K, then she can reconstruct what the message would have been. So long as they both know this one-time pad, this K on either end, you can encrypt a message using that and send it over this channel, and Eve, the NSA, will not be able to tell what the original message said. Of course, they can run through all the options, and in this case, there's 2 to the 7 options because the bit string is length 7, which is a small enough number that they could do it. But in practice, our one-time pad, our key, will be sort of 128 bits long rather than 7. Okay, I'll just give you a second to digest that before I move on. And if anyone needs a clarification, then please put in the Q&A and Catherine can ask about that. Okay, hopefully you've had long enough to digest how this works. So before I talk about how to get this K on both sides, I want to just have a little sort of commercial break, talk about what I believe is one of the most successful examples of using this very simple encryption technique with one-time pads in history. And that is the underground movement against apartheid in South Africa. So in the middle here, you've got this picture that says the Vula Connection. So the Vula Connection is the name of a documentary about this underground encrypted messaging movement to end apartheid in South Africa. It's free on YouTube. You can watch it. It's 1 hour long if you're interested. And it's a really incredible example of how cryptography can be used for the greater good. So what they did with this system is they coordinated their efforts across the whole country by sending each other encrypted messages before that was really widely known about how to do, because this was, in the 70s and the 80s. And the culmination of their efforts was to raise awareness of apartheid, especially among white South Africans. I mean, Black South Africans were probably fairly aware that their lives were not great, but a lot of the white South Africans didn't really know what was going on. And so they got a lot more support from white South Africans in the politically from spreading the messages around, but also about just generally what they were doing in the movement. And I would say the biggest success, the sort of end point of this underground movement, was getting Nelson Mandela out of prison. So the top right picture there, you can see him in his political prison. And the way that they did this is that they really used only one-time pads. So they sent messages to other people in the movement. There was some people coordinating who decided what the movement was going to do in that week, with keys, encrypting the message in the way I just showed you on the previous slide. And the way that they got the keys to each other, because they had to change them every few days just to be safe, is that there was a air hostess who worked for the Dutch airline KLM, who flew every week with her job from Amsterdam to Johannesburg. And this was being coordinated from London, and there was obviously connections between London and Amsterdam weren't so monitored. And she brought a big suitcase full of physical lists of numbers, either on a computer or on a hard drive or just written down, which were then distributed around the country. And she wasn't checked as an air hostess, as a member of staff. And this had the one-time pads that they used for their encrypted messaging. So it is a big success, because once they started using this method, they stopped getting caught as often. They were still caught once, and there's a moment in the documentary about that, because it can still be intercepted. But it was definitely a big success story for how this can be used for encryption. But there's a very big downside to using this idea for sort of less sensitive operations, like sending messages to your partner or family that you maybe want to be a bit private on WhatsApp or something, which is that how do you share these keys without having an air hostess bringing them to you every week, or something along those lines, in a way that's actually efficient, that we can really use in our day-to-day life, right? So here's a bunch of things that maybe use all of them, maybe use some of them. So it's Google, WhatsApp, Facebook, Signal, online banking, chips in your contactless payment cards. All of these things use encryption, and they use a combination of something similar to the one-time pad method and a key sharing step. But yeah, so all of them require sharing a key K securely, so that can be used as, for example, as a one-time pad. But the current methods of sharing K require a lot of mathematical structure. So we rely on a maths problem that we know to be hard to solve. And this structure is something that can be very directly exploited by quantum computers using known quantum algorithms in the future, once quantum computers get to the stage where they're both large and stable enough to be able to basically solve these maths problems in an exponentially less time than can be solved on a classical computer. And that structure that's involved in sharing this key is the fundamental thing here. So that one-time pad thing, that part is actually not really that affected by quantum algorithms, but the key sharing part is something that's sort of devastatingly affected, at least the methods that are used in all of these examples that I had on this slide, and most of our day-to-day interactions. Okay, but that sounds a bit doom and gloom. But, well, my research and my students and other people in the department is about something called post-quantum cryptography, which is about solving this problem. So we're in a similar situation where we've got a sender and a receiver, an insecure channel with an eavesdropper. This is the NSA again, who we call Eve. But now we have slightly different assumptions, which is that we suppose that Eve has a quantum computer, but the sender and the receiver don't have a quantum computer. They just have, you know, in the examples that I gave, it's Google, they have a computer or a smartphone. If it's online banking, they have a smartphone or maybe even just a chip in a card. So they've got very, very low computing power that's, you know, something that we can do today. But Eve has access to a quantum computer. So this sounds like a difficult problem, and it is a fairly difficult problem, but there's quite a lot of ideas for how to replace this, replace this mathematical structure that's used to compute the key with essentially a different type of mathematical structure that doesn't have what you need for the quantum computer to exploit it. At least that's what we hope. So I'm not going to go into details on that, but you're welcome to ask me about the details in the Q&A. But just to give you a sort of overview of where we are, so the discussion is currently dominated by the NIST, that's the National Institute for Standards of Technology in the USA. They've been running a competition for a few years since the end of 2016 for post-quantum standardization. And this is after their government report with this key finding 10, which I'll read out. Even if a quantum computer that can decrypt current cryptographic ciphers is more than a decade off, the hazard of such a machine is high enough and the time frame for transitioning to a new security protocol is sufficiently long and uncertain that prioritization of the development, standardization, and deployment of post-quantum cryptography is critical for minimizing the chance of a potential security and privacy disaster. So I think this sort of basically sums up the feeling in the community of the people doing research in post-quantum cryptography, which is, as I was saying at the beginning, especially since, you know, powerful adversaries are storing our data already, it's the more we can do, the sooner the better, essentially to protect against this upcoming change. Okay, so what has happened since they started this competition? Well, they got 82 submissions, so that's a lot of ideas. Obviously, not all of them were good, but there were a lot of good ideas in there, and there's 5 different sort of mathematical concepts on which these ideas are based. So hopefully there's enough variety that at least one of them won't be broken. So there's 15 submissions currently in the 3rd round, and they're trying to keep some of the different mathematical ideas in there with a view to the fact that they're all quite new, and it's quite likely that somebody comes up with either a classical or a quantum algorithm to break these things. So aiming for a total of 4 rounds standardization next year, although with Corona, maybe that will be a little bit postponed. But this only covers digital signatures, so that's about authenticating your identity, and key encapsulation. So that is a little bit like the sharing key securely that we talked about earlier on, which you can then combine with some other ideas to turn into, for example, a messaging protocol. So these are the 2 fundamental things that we really, really use every day, but it doesn't cover everything that we use currently on the internet. So there's definitely still quite a long way to go in terms of preparing ourselves as a community for this upcoming change. So yeah, so here's what we're still doing as a community and the open problems and research directions that we're working on. So thorough cryptanalysis, that just means trying to break stuff, both classical and quantum. So that's both trying to break something on a classical computer, because these are all algorithms that you can run on a classical computer, if you remember, and trying to break something on a quantum computer, which obviously is fundamental for a post-quantum cryptographic scheme. And different schemes have had different levels of cryptanalysis. But for example, one of the submissions that's in the third round of the NIST competition was had a fairly large attack only a few months ago. So there's definitely still ideas out there which haven't been found. A secure and efficient implementation, especially considering hardware limitations. So this is really fundamental for having something adopted in industry. So with post-quantum standards, they're all, like I say, they're all fairly new. There's been much less work on developing those than there has been on the stuff that we're currently using, as you might expect. And as a result, everything that you might use is either slower than what we currently use, or it uses more memory than we currently use. If it uses more memory, it needs a larger chip, and that's more expensive. So in order to convince companies who maybe don't have the technical expertise working for them to understand the security risk, to deploy this on a wide scale, we need to get our algorithms to the stage where they're competitive with what we're currently using, and also mitigate the security risk of quantum technologies. And that's quite a long, to the stage we're currently using is a long way off, but we're doing our best. A meaningful comparison between candidates. So if you remember on the previous slide, I said there are 15 candidates still in the third round, and it's quite hard to compare which one is the best for different use cases, just because it's been a sort of free for all so far, where everybody does their 2 cents, and we don't have, for example, on this device, here's an implementation of each idea, which one is the best. So it'll be very different for a chip on a smart card than it will be for a laptop, for example. And then, the fourth thing I already touched on when I was talking on the previous slide, more advanced protocols. So a lot of the privacy preserving protocols use quite advanced cryptographic functionality, which is something that we currently don't really know how to do in a way that's post-quantum secure. If you're in this world, you may have heard some sexy terms like zero knowledge, which are also exciting things we can do and are used in some applications, but we can't do those things in a post-quantum secure way. So if we become too reliant on those things as a community, then that can cause a problem. For example, it can cause a problem in sort of cryptocurrency type applications. Okay, so I think that's my 20 minutes. So if there's any questions, I'd be very happy to elaborate on any of those things or clarify anything that you might want to ask about.
Chloe, thank you very much for that talk and that really useful introduction to cryptography. Could you just explain a little bit more about what zero knowledge is?
Yeah, absolutely. So it sounds a bit strange. So it's the very down-to-earth sort of explanation of what zero knowledge is that you can prove that you know something without really revealing what that thing is. So in a sort of basic example is to prove that you are who you say you are without revealing your identity. But you might also want to prove that you have certain characteristics without revealing details about those characteristics. So actually an example that my colleague came up with the other day asked the same question is, so if you're comparing, you want to know which of me or him earns more money, but neither of us want to reveal our actual salary. But you can look at the fact that he's got a senior in front of his name and I haven't. So therefore he will earn more money. So you're not revealing any more than you want to reveal.
Great, that's really clear, thank you. So Sophie in the audience says that was great. Are there companies that are getting involved in this work at the moment, and are you engaging with them directly?
Thanks, Sophie, for the question. So yes, there are definitely companies that are getting involved, and I personally am engaged with a couple of different ones. So there's a few actually specialist companies who are very specifically working on post-quantum cryptography. For example, PQ Shield in Oxford, who I work with quite a lot. But also a lot of the bigger companies are very involved in developing these ideas and trying to update their own technologies to match that. So for example, I work quite closely with IBM Research, where there's a researcher who's working on the same small field of post-quantum cryptography as I am. Facebook are investing in it, Microsoft are investing in it. So it's definitely something that a lot of the big companies are very aware is something that they need to invest and change their systems, which is great. I think the hardest thing that's going to be the hardest sort of goal for the community at the moment is to get the sort of small to medium companies who maybe don't have as much free investment fund to get specialist teams on to work on this, to have standards that they can use, and to also have, enough open source material for people to educate themselves on how to make the change to a post-quantum secure environment.
Thank you. Another couple of questions. So one from Lee. The RSA algorithm used for PKI is vulnerable to Shor's algorithm, whereas AES used for blockchaining is vulnerable to Grover's algorithm. Can you comment on the expected time frame for quantum computers to be capable?
Absolutely. So this is very true. So just so that everybody else is on the same page. So Shor's algorithm applied to RSA, which is used for many things, and used, for example, by basically every bank. So that is what's called a polynomial time quantum algorithm, meaning that the amount of time to encrypt your data on a classical computer will be roughly the same amount of time needed to decrypt your data on a quantum computer once a quantum computer is big enough. So that's quite a devastating algorithm. Whereas Grover's algorithm applied to something like AES, which is used for blockchain, as you say, but it's also used for basically every messaging protocol as a step. This is actually not that devastating. So it is more efficient than the best known algorithm we have at the moment, but it's only what we call a square root speed up, meaning that the decryption algorithm will be faster than it currently is, but it will still be very, very much slower, enough slower than the encryption, that you've got that separation that you need to have an encrypted algorithm. Okay, so to actually answer your question, in order to apply Shor's algorithm to RSA, you need, in order to apply Shor's algorithm to the instances that are of RSA that are currently used on your devices, you need a quantum computer which can run about, let me try and get this correct, I think it's 2,000 to 3,000 qubits. And those are logical qubits, which need to also stay stable for long enough for the algorithm to run. So that's really quite a long way off, I would say, given that currently we're looking at sort of 50 to 100. And so it's really hard to say. It's really hard to give an accurate prediction how long it will take for quantum computers to reach that kind of size. But if you assume that it will continue improving at the rate it has been improving, then you're looking at sort of a timescale of 50 to 60 years. But what you might not have heard of is there are different types of encryption used for different applications. So for example, your messages, if you use WhatsApp or Signal on your phone, that doesn't actually use RSA, but it uses something called elliptic curve cryptography. And the reason it uses that is that has much lower memory requirements than RSA. And so on anything that you want to try and fit on a small device like this one, or an even smaller device like a chip, elliptic curve cryptography is normally the thing that's used because it's much smaller than RSA. But the fact that it's much smaller than RSA, it's also susceptible to Shor's algorithm, and that also means that you need a much smaller quantum computer to attack it. So for devices that are using elliptic curve cryptography, we're looking at a shorter time frame, which again, it's impossible to make a very accurate prediction, but it could be sort of anything between 10 and 40, where the middle of that is the most likely. But 10 years is obviously quite soon. So if it does end up being the shorter end of that, then you want to be fairly prepared. Now, for running Grover's algorithm, that's actually a shorter time frame, but as I said, it's much less devastating because it doesn't actually destroy the viability of the crypto system. And in fact, what's currently being put forward by NIST, for example, for AES is to not even change the parameter sizes for the quantum algorithm, because running an algorithm on a quantum computer is sufficiently more difficult than running on a classical computer that they think that separation won't even affect how secure the system is.
Thank you, Chloe. Abada has asked, when you were discussing post-quantum cryptography, you said that we assume that Eve has a quantum computer, but Alice and Bob don't. What would change if Alice and Bob did have quantum computers?
Okay, it's a good question. So with post-quantum cryptography, because we want to test all of our algorithms to make sure that they're sort of robust as possible, we're not really thinking very much about whether or not what you can do if you have a quantum computer. But in some situations, for example, with digital signatures, which is about sort of authenticating your identity, which is not about which is more about what happens in the moment than about decrypting things in years to come. There, sometimes we do want to think about what we can help with quantum computers, and often that means that the algorithm that I just said it's very slow compared to the state of the art at the moment. You can sometimes use quantum computers to speed up that algorithm in quite a big way. So that's one answer to your question. Another answer to your question, which is so I'm going to change your question slightly just to bring this up, because I do think it's an important thing to say, which is what happens if both Alice and Bob, or Megan and Harry in my example, and Eve have access to quantum technologies, which is obviously a little bit more general than saying quantum computer. So another solution that's being put forward for this problem that I've outlined is something called quantum key distribution, which I'm sure some of you in the audience are very familiar with, which involves setting up a sort of physical link between two parties who want to exchange secure messages and then you really use quantum technology to encrypt that message. And I think that for sort of secure messages between powerful people like governments or big companies, this is probably going to be a very good method to use, because the technology develops at the same speed as the ability to decrypt it. But for your average person who can't afford to set up a quantum line from their house to everybody they want to speak to, that's maybe a little bit infeasible. And also, if you want to do wireless communication, which we're all completely used to by now, then that is also quite infeasible. So there are sort of different ways of looking at that, how to make use of. It's a nice positive question. I like it. How to make use of the quantum technology as a user.
Thank you. And the next question actually is really leads directly onto that. So Emilio thanks you for your introduction to crypto and said, what is your view on the integration of QKD and post-quantum cryptography, and which cases would it be useful to combine the two? I don't know if you want to add more to the question that or the answer you've already given.
Yeah, so Emilio, thanks for the question. So I think Emilio is actually working on QKD, if it's the Emilio, I think it is. So I do think that there's definitely some scope in the long term for cryptographers and people working on QKD to work together, especially for people who've been looking at something called side channel attacks. So this is something that already exists as a attack avenue for classical cryptography, which is looking at sort of computer data for if somebody's encrypting something on their own laptop in their own house before it gets sent over the channel. Sometimes you can deduce some information from that. For example, from how much power their computer's using, or how long it takes to encrypt something. You can deduce something about the kind of data that's being encrypted. And some sort of beginning experiments on quantum key distribution has shown that the quantum key distribution ideas are actually vulnerable to the same kind of thing. Although we initially thought it should be quite resistant to side channels, because if you intercept the message, then your qubits will collapse because they've been observed. And then, I mean, you don't get your message, but also it's, you know that it's been tampered with, unlike with a classical thing. But if you're really looking at the machine that's encrypting it rather than trying to intercept it in the wire, you can learn some things from side channels. And I think that if the people who are working on quantum key distribution and the people who are working on classical side channels talk to each other, then this is something that we can definitely try and solve as a community.
Great. And Emilio has confirmed he is working on QKD.
Okay.
That's great. Perhaps one final question, Chloe, is how do the post-quantum systems that have been put forward compare to the ones that we're currently working with?
Yeah, so it's really the post-quantum stuff is worse. That's the short answer. So that I hope that there's something for every application. So there's, as I said, there's sort of 5 different mathematical ideas, and each of these ideas comes with an upside and a downside. So most of my research is on something called isogeny-based cryptography, and it's the big downside of isogeny-based cryptography is that it's much slower than what we're currently using, sort of 100 times slower than what we're currently using. But some of the schemes are as small as elliptic curve cryptography, which I mentioned is something that is used on small devices, because of memory reasons. We don't even want to use something like RSA. But there are other schemes. So for example, lattice-based cryptography, which is another field that is very, very fast. That's as fast as elliptic curve cryptography, which again is the fastest thing to do this key distribution thing. But the keys are 1,000 times as big as elliptic curve cryptography. But if you're then doing something on a laptop, for example, where you've got lots of memory anyway, and it's not more expensive to use it, then you can just use lattice-based cryptography, and that's no problem. If you're trying to fit something onto a very small device, so maybe some of you have come across buzzwords like Internet of Things, then you know that you have to pay for that a little bit with time. You have to do that with classical cryptography anyway. So hopefully these very small memory ideas will be enough to will be fast enough for the applications there. But there's a few trade-offs as well that are in between, but you basically are always paying for the security with either speed or memory. And there's currently not an idea for how to get both as good as we currently have. Although, who knows? Only time will tell if we manage to get there.
That's great. So we're fast approaching the end of our session, and you've answered all of the questions that have come up in from the audience. So I'll bring the session to a close. Many thanks to everybody for attending and for your questions. It's really been an interesting introduction to both cryptography pre-quantum and post-quantum. So thank you, Chloe, for giving that presentation. In the current climate, unfortunately, online is the only way that we're able to showcase our research capabilities. And we appreciate that that doesn't really allow for the kind of conversations that we'd really like to be able to support and initiate. But if you have been really interested in what you've heard today or throughout the week, if you've been attending any of the other activities as part of the showcase event, please do get in touch with us. The Industrial Liaison Office is here to connect industry with our students and our academics, and we'll be sending out our contact details after the showcase event so that you can get in touch. But in the meantime, many thanks for attending, and have a good rest of the day.